Good morning, everyone. Today I will present our work on the application of deep learning techniques for fault diagnosis in wind turbine using vibration signals. As wind energy continues to expand worldwide, ensure the reliability of wind turbine has become increasingly important. Our work investigates how artificial intelligence can automatically identify mechanical faults from vibration measurement, reducing maintenance costs and improving system reliability. Wind turbines are complex electromechanical systems that operate continuously under highly variable environmental conditions, including fluctuating wind speed, temperature change, humidity, and mechanical loads. These operating conditions place considerable stress on critical components such as gearbox, bearings, shaft, and generator. Failures in these components can lead to unexpected shutdown, costly repairs, and significant production losses. For this reason, the wind energy sector is moving from traditional corrective maintenance toward predictive maintenance, where faults are detected at an early stage before severe damage occurs. Among the different monitoring techniques available, vibration analysis has proven to be one of the most informative because mechanical defects produce characteristic vibration signatures long before catastrophic failures. In this work, we investigate how deep learning techniques can automatically analyze vibration data collected from wind turbines, eliminating the needs for manual feature extraction and providing a more robust and intelligent fault diagnosis framework. Wind turbines are designed to operate continuously from more than 20 years, often in harsh environmental conditions. During their lifetime, they are exposed to highly variable wind loads, changing temperatures, humidity, and continuous mechanical vibrations. These operating conditions generate progressive degradation of several mechanical components. The gearbox, bearing, shaft, and generator are particularly susceptible to fatigue, misalignment, lubrication problems, and surface wear. Even relatively small defects can gradually propagate until they result in serious failures. When a major component fails, the turbine may remain out of service for several days or even weeks. Besides the cost of replacing damaged parts, operators also experience significant economic losses due to interrupted energy production. In offshore wind farms, maintenance interventions are even more expensive because of the logistical challenges associated with accessing the turbine. For this reason, modern maintenance strategies increasingly rely on a condition monitoring system capable of identifying abnormal operating conditions before catastrophic failures occur. Detecting faults at an early stage allows maintenance activities to be scheduled proactively, reducing both repair costs and turbine downtime while improving the overall reliability of the wind farm. Among different techniques available for monitoring wind turbines, vibration analysis has become one of the most widely adopted because of its sensitivity to mechanical defect. Whenever a fault begins to develop, for example a crack in a bearing raceway, a damaged gear tooth, or shaft misalignment, the dynamic behavior of the rotating system changes. Dizzy change generates specific vibration signatures that can often be detected long before the failure becomes critical. Modern turbines are equipped with accelerometers installed near strategic mechanical components. This sensor continuously measures vibration during normal operation, providing a large amount of information about the machine health. Traditionally, engineering analyzed these signals by extracting handcrafted features in either the time or frequency domain, such as RMS value, kurtosis, crest factor, or spectral peaks obtained through Fourier analysis. Although these methods have been successfully applied for many years, they strongly depend on expert knowledge and may struggle when operating conditions vary significantly. The data used in this work are obtained from the Turbines Supervisor Control and Data Acquisition Systems. SCA data systems are already installed in most modern wind farms and continuously monitor both the operational status and the health of each turbine. Every measurement is automatically stored in a centralized database, creating a valuable historical record that can be exploited from predictive maintenance. Our framework primarily focuses on vibration measurement acquired from sensors installed on critical mechanical components. These signals are complemented by additional operational variables such as wind speed, rotor speed, generator speed, power output, and temperature. Combining vibration information with operating conditions provide a more comprehensive representation of turbines' behavior. The resulting dataset contains a large volume of time series data collected under different operating conditions, including both health and fault states. This makes it particularly suitable for training deep learning models capable of recognizing complex patterns associated with different types of mechanical fault. Before training the deep learning model, the vibration signal undergoes several preprocessing steps to improve their quality and ensure consistent input data. The first step consists of reducing measurement noise and removing unwanted disturbances that may affect the signals. Depending on the application, this can be achieved through appropriate digital filtering techniques while preserving the frequency component associated with the mechanical fault. Next, the signals are normalized, since vibration amplitude can vary considerably under different operating conditions. Normalization ensures that all samples are represented within a comparable numerical range. These improve the stability and convergence of the training process. The continuous vibration recordings are then divided into fixed length time windows. Each window represents an individual sample that contains sufficient information about the dynamic behavior of the turbine during a specific time interval. This segmentation process also increases the number of available training samples, which is particularly beneficial for deep learning. The final output of the preprocessing stage is a structured dataset composed of standardized vibration segments that can be directly used as input for the neural network architecture. The process begins with vibration data collected from the SCADA system. After preprocessing, the segmented signals are provided as input to the deep learning models. Unlike conventional machine learning approach, where experts manually define the most informative features, deep learning automatically discovers representative patterns directly from the data. This significantly reduces the dependence on prior domain knowledge and allow the model to adapt to complex operating conditions. Two different neural network architectures are investigated in this study. The first is a convolutional neural network, while the second combines CNN with a long short-term memory network. The output of the framework is the predicted health condition of the wind turbine, enabling the automatic identification of different fault categories and supporting predictive maintenance decisions. The first model is the convolutional neural network. CNN have become one of the most successful deep learning techniques because they automatically identify local patterns within the input data through convolutional filters. In vibration analysis, these filters learn characteristic signatures associated with different mechanical faults. However, vibration signals are not only characterized by local features, but also by their temporal evolution. For this reason, we also investigate an hybrid CNN-LSTM architecture. In this model, the CNN first extracts the most informative feature from each vibration segment. These features are then processed by the LSTM layer, which model temporal relationship and long-term dependencies with the signals. This combination allows the network to exploit both spatial and temporal information, potentially improving classification accuracy. The performance of both architectures is then evaluated and compared using standard classification metrics. The experimental result confirm the effectiveness of the proposed methodology. The deep learning model successfully distinguished between health operating conditions and different fault categories using only vibration data. The classification performance was evaluated using common metrics such as accuracy, recall, and F1 score. A confusion matrix was also analyzed to better understand the classification behavior for each fault class and to identify possible sources of misclassification. Overall, both neural network architecture achieved high diagnostic performance. However, the hybrid CNN-LSTM generally provides better results because it combines the powerful feature extraction capability of CNN with the temporal modeling capability of LSTM networks. This finding demonstrates that deep learning represents a reliable solution for automatic fault diagnosis in modern wind turbines. Beyond achieving high classification accuracy, the proposed framework offers significant practical benefit for the wind energy industry. By continuously analyzing the vibration signal, the system can detect early signs of mechanical degradation before fault evolve into critical failures. To conclude, this work demonstrates the potential of deep learning for intelligent fault diagnosis in wind turbine using vibration signals collected through SCADA data system. Unlike conventional approach, the proposed framework automatically learns representative fault features directly from the data, reducing the need for manual feature engineering and improving diagnostic performance under variable operating conditions. The obtained result confirmed that deep learning method, particular hybrid CNN-LSTM architecture, can provide accurate and reliable fault classification, supporting predictive maintenance strategy and increasing the operational reliability of wind turbines. Future research will focus on several directions. First, we plan to investigate more advanced deep learning architecture, including transformer-based model, to better capture long-range temporal dependency with vibration signals. Another important object is the implementation of real-time monitoring system capable of continuous processor streaming SCADA data In addition, we aim to integrate explainable artificial intelligence techniques to improve the interpretability of the diagnostic decision, increasing the confidence of maintenance engineering in AI-based systems. Finally, combining deep learning with digital twins and edge computing could enable the next generation of intelligent autonomous monitoring system for renewable energy infrastructure. Thank you very much for your attention.